Alrighty then.
Well,
In the assignment for today,
math class.
what problems do we have to take a look at?
43.
61.
89.
69. Yeah.
Dylan, will you copy the numbers down?
Yeah.
Okay, and then give them to him.
Oh,
He's picked up a couple,
But seriously,
and,
65.
okay?
Good job, Chanel. Good job, Chanel.
While we're getting that ready,
What did you find?
I didn't get A.
give Dylan the question numbers again.
65. Mainly A.
69.
No, go 60.
69.
61.
83.
We don't have 83.
43. 43. 12 and a half. 12.5.
Marlo, 61.
Oh, thanks. I think we give them like.
Here you go.
Oh, I forgot to write my name earlier. Oh, it's just a midpoint deal. Okay, you gotta split it into 3 intervals, and then here you go, dear bear.
Are you doing B?
Okay. Today, I'm going to spend most of my period doing the fundamental theorem of the calculus. I think we're ready for it. Monday's a good day to get this completed. The problems that Dylan has copied, I will try to take care of on Wednesday. Okay? Wednesday, we have a block schedule. And so, I want to show you, and I'll develop this also a little bit more on Wednesday, but this is what it says. And this is the guy that I taught the book of the last time I taught calculus, and by the name of Stewart, an excellent writer, and he says this: the fundamental theorem of the calculus is unquestionably the most important theorem in calculus. You notice we've had some. And this is what he says. And indeed, it ranks as one of the great accomplishments of the human mind. And I happen to agree with him. It was an amazing feat, okay? Before it was discovered from the time of Archimedes, and I put his date there. And we'll take a look at some other mathematicians. To the time of Galileo and Fermat, problems of finding area, volume, and lengths of curves were so difficult that only a genius could meet the challenge. At this point, you can only do straight lines, walls, and simple kinds of stuff. And anything that has a curve, you have great trouble. Except for some little ones like spheres. Circles and spheres, you had a nice 6th grade or 7th grade teacher that taught you some things about pi, so you could handle a few of those. Okay? Now, but now armed with a systematic method that Newton and Leibniz fashioned out of the fundamental theorem, we will see that these challenging problems are accessible to all of us. And so I'm really excited about doing this thing. We have gotten a little bit of a look at it already. And this is big time stuff. Okay? So here we go. A couple review ideas. This one. This is on page 324. We have this defined. The integral from a to b of f of x dx, he says, is going to be like the Riemann sum. And see what you can find here that's different in what your book gives and what I'm giving. N is going to be approaching infinity of this summation from k equals 1 to n of f of x bar k, like this, delta x sub k. Now, what is different about this one than the book? Yes?
Your limit is different.
This you said is different?
Yeah.
How is it different?
In the book, it's the limit of delta approaching 0.
Okay, now, did you hear what she said? I prefer this. If you write the other one, I don't have a problem. But delta is a change. And I like this much better, because this is telling me that my intervals of my Riemann sums are going to infinity. Okay? I'm going to have an infinite number of these little intervals. Okay? Now, James, what does this mean right here? You don't know. Okay, now, this whole business here is the Riemann sums. It's adding all those, and we have done this with our calculators, doing the calculations of some of them. We didn't go to infinity, of course, because we couldn't. We didn't have the time for that. Infinity takes too long. It's forever. Okay, now, go ahead. What?
The interval, right?
This is the interval. This is the width. This is the width of the interval.
And that's the actual Riemann
That's
sum.
right, left, or
Okay, Dylan, once again, he says, and he's using a combination of things here. He says this is right, left, or middle, or someplace in there. And of what interval is this height given? The kth interval. We're breaking up this into many, many little parts, and this is the width of them, and that's the height of them. Okay? Any questions about that? Okay? Then the next thing I'd like to do is to go to page 335, I think. Yes, 335, bottom of the page. Definition, area function. And that area function goes something like this. I'm going to get this here over here. And now, that thing says this area, A at x, that area there, is going to be defined to be the interval, and you notice this is a t, and that's it, f of t.
Yes.
DeVries? See that what we have here?
Yeah.
So this is going to be, and notice here, now you aren't watching. Okay, this is an A, and we're going to run to x. Okay, we're starting here and going this way. This is going to be defined as this area, which is now f of t dt. Okay? See how that, I think, yeah, I have everything right. On the bottom of page 335. That's a definition. Okay?
Mr.
Yes.
So then what's up with, there's like three graphs, they all have the same function. One's A to B, one's A to C, and then the other one's A to C with negative C to D on it. Like, can you explain that?
Okay, what page are you on?
On 335, it's like the middle of the page.
Okay, let's go up there. I'll try to do a little bit. Let's see, that's there. You see. Thanks for asking the question. It's messing me up a little bit, but that's what we want to do. That's where you're at. Okay, now the first one, it says we're going to go from A to B.
Yeah.
Okay, and that's that blue area, and it is defined to be the area. And, oh, I can do a bunch of things there. Look here. You notice it says A at B.
Yep.
And that means we're going to run up to here. So we're going to go this way, B, F of T, dt. So we have that blue area in the first one. Okay, now the second one, we're going to go to a different point. We're going to go to C. So this is A at C. I don't believe you have any trouble there.
Right.
Okay, but now the next one, you're going to go all the way to D.
Yep.
And you notice that the second part is underneath, and dealing with the net area, we have to subtract that one away. So what he does there is he says A at D means going all the way. Now this is all going to be changing by the end of this class period. Okay? This is good, but it's going to change. Now we're going to go all the way from A to D, and A is at 0, and we're going to do the positive parts from A to C. You notice that's where it crosses the axis.
Yeah.
F of t, dt, and then we're going to subtract that because we're talking about net area.
You can add them though too, can't
Oh,
you?
okay.
It's a
He wants to
negative.
add them, and he's going to add from C to D this is all right, like this dt. Okay, so that's what he does it. Derek?
When it's below the x-axis, is your value still positive though?
No, your values are
It
going to be
is
negative.
Okay.
Your reading on sums are going to be negative. Okay? Now, let's see here. Anything else I want to do? No. Okay, now, the next thing I want to do is get that little graph up here again. And I thought this is where Grant was going to go. See, this area is from here to here. Okay? Well, basically, you'll see this on page 337, but I'm going to be doing more things on page where am I? 344. Okay? So hang on. Here we go. Let's see here. First off, I'm going to make another line over here, up and down. And this is h. And this point over here is x plus h. Okay? Now, probably before I go there, I would like to write something else up here that might be helpful in a few minutes. Can you tell me what this is equal to? The limit as h approaches 0 of a at x plus h minus a at x all over h. What is that equal to? I've heard it, a lot of people said it was this. Okay? Any questions about that? Okay, now, the next thing I'm going to do is use what I just had up there a few minutes ago in terms of definition. I'm going to take this area from here to here, so I'll write that down, and that's going to be a at x plus h, and I'm going to subtract this part away from it, subtract like this, and you notice what I have then. I've taken all of this, and so I only have this little area left, right? See it? So I'm going to say
So isn't that just
that's going to be approximately equal to h times f at x. Now, at this point, I can choose any x between there that I want. It's going to vary in terms of, but it's just approximate. It could be this one, it could be all the way over here. It's some, well, in this case, I'm actually saying it's going to be this height across here, and so this area is approximately equal to this. Got it? Okay, now, this is what I'm going to do. I'm going to divide both of these by h, and so I have this, and then you'll see something else that I'm going to do, and this is pretty amazing what I have here. This is approximately equal to f at x, like this. Yes?
Is this a proof?
Hmm?
Is this a proof?
Oh yes, this is a proof. Oh yes, I'm on my way. And this is the first part of the fundamental theorem of the calculus. Okay? Now, what I'm going to do here is I'm going to take the limit of this as h approaches 0, and here, I'll do it this way too, the limit as h approaches 0 of f at x, like this. Okay, now, what is this equal to? Coming not that way, but this way. This is a prime of x. And this is an amazing thing that's happening here. It's unfolding right before your eyes. I don't have this done yet, but I think I have enough room, so I'll just go a little lower and keep going for a little bit. Okay? So, now, I have this quantity over here equal to this. Now I'm going to do something else. And I'm going to take really this statement here once again. I'm going to take this statement now, like this, x plus h. Because see, it's approximately equal to this over here. See that? It's an approximate. I don't like approximations here. So I'm going to take this, minus a at x, like this, and I'm going to say that now that's this area. Okay, now would you watch this for just a second here? I have this area right here, see this here? That's this area right in here. I'm going to say this is going to be the minimum amount. That's the lowest part. And up here is going to be the highest part. See that? And this is going to give me a minimum, and this is going to give me a maximum. Whatever's in there, I'll take the lowest point and the highest point, and I know I can do that. Because I'm going to be the mean value theorem and a few other things that I've done. I know there's a low point and a high point. So, this here area is going to be less than or equal to the maximum times h, and on this side it's going to be the minimum times h. Now I have a moment for you to catch up and ask questions.
This proof is called what now?
Fundamental theorem of the calculus. You notice I should give you the fundamental theorem of the algebra. That sucker is so hard that we can't even do it without having two semesters of calculus.
What?
This one here we can do right now, even though it's such a powerful, wonderful theorem. Okay?
So what does this mean then?
Oh, it'll come. Yes.
What did your last line say there? Those two M's.
This is the minimum height. The minimum height here, and this is the maximum height times h, this distance.
Okay.
Chanel?
You have on the graph, is that x plus h in orange?
Yes, this is x plus h.
And that's referring to,
That's this point, x plus h.
okay.
Okay, this is the h. Okay, very good. Okay, now, yes.
Is one a little, the minimum is like lowercase m and then you have an uppercase m?
Yeah, this is the itty bitty little one, this is a great big one. Okay? This is the maximum in between, and this is the minimum. So, go ahead.
Can you go over that bit again?
Okay, now, a while ago, I just defined this area here to be that integral from this point to this
Yeah.
point with a t in here. Okay, so I'm kind of working in there now. And this area right here, this area, is going to be h is the width,
Yeah.
and the height is going to be everywhere from the lowest point to the highest point. Okay, and this is the highest point, this is the lowest point. Okay, now, yes.
What is the t for?
What is the t over here for?
Yeah.
This is the t-axis.
Oh.
That was just the t-axis a while ago. Yes.
I don't know.
Okay, now, I'm going to take the limit of this.
How come in the second one there, you approximate it to be h times the f of x? If
Here?
Yeah, if it's in between.
Okay.
1 and x.
Okay, her question is here. We're now at this point, but let's go back up here. Now, I'm saying that the difference between the area up to here and here, in other words, that distance, is approximately h times any f of x in between here. Now, I just used f of x, probably meaning this point right here. It could be here, but it could be any point in between also. Okay, but this would be one of the approximations. Okay, somewhat close. Okay, now watch what happens. I'm going to take the limit of everything, and but before that, do everything. I'm going to divide everything by h. I think that'll work. This is h. Pardon? Oh yeah. Oh, now Trevor over here. He says, "Oh, but Kramer, you are already here at a prime." Okay, that's very good to notice. But now, Trevor, I'm going to work on the other side. And that's going to be the amazing part. You're going to see something happen in a minute. Okay? Now, so, these cancel like this. And now I'm going to do that limit like I did here. I'm not going this way at this point. I'm here, and I'm going to go this way if I can. Okay? So, this gives me the limit of little m as h approaches 0. What is that equal to?
Little m.
Okay, that's the smallest one in here, and when x is going to be equal to 0, this quantity is nothing more than f of x. Because I'm squeezing all the life out of the thing. So I'm going to be right here, okay? And this here in between now is going to be the limit of a times x plus h minus a at x all over h as h approaches 0. And on this side, I'm going to have is less than or equal to the limit of big M as h approaches 0. And what's this going to be equal to?
F of x.
That's going to be f of x. So what have I done?
Okay.
Yeah, I squeeze. I have f of x on this and on this side. So this is equal to f of x. Okay?
As it approaches 0.
Yes, as it approaches 0. Yes.
Okay, so then.
Just a second.
So where did you get these less than or equal to signs from?
Okay, out of here. I know that in between here, this is my function wiggling around. I don't care how it wiggles. There's going to be a low point and a high point. Okay, and this is the smallest one, and this is going to be the biggest. And then what I do is I squeeze them together.
So
Yeah.
your limit of, so your M, is that what you're saying is your M are on either side of the X? Like, so the points are coming closer to X?
Yes, but I wouldn't go either side. When I take this here h and bring her right back up to here,
Yeah.
really, really close, there's no difference between the maximum and minimum. If it's not close enough, get it closer. If it's still not close enough, get it closer yet.
But what you're saying is that a limit of okay, so what is M?
M is the highest, the biggest f of x. Up here. That's the biggest f of x.
Oh, so are we going with the Y here, not?
Oh, you got that? Yes, this is the y.
So we're not dealing with 2 points? We're
No,
dealing with
well,
one line, right, kind of?
yes, we're actually dealing with a Riemann sum.
Okay.
Okay, a while ago when we were doing this integral stuff, or excuse me, the derivative stuff, we were always using these secant lines. Now we're using all these little Riemann sums. And this is really a tiny, tiny, tiny Riemann sum. Okay? And now, look what happens here. We have said this. I'm going to go up this way so I think you can see it a little bit better. This quantity here, let's see, I will write this way. H approaching 0 of h at x plus h minus a at x all over h. Okay, now, I just said this was equal to f at x. See that? But Trevor, a moment ago, said, hey, you said it was over here like this. So you see that? Yes. Okay. Now, I believe I'll leave this here a minute. I'll just do a little writing on the board. Shall I just erase this?
No, not yet.
Can you take it over there? Okay. You know this, that if I had f at x like this, from a to b, dx, do I want that there or not? No, I'm going to erase something first a minute. If I have this, you know how to solve this thing.
Yeah.
What is this equal to? Well, that's equal to f at x what?
D? No.
Okay, let me just use a problem over here for you. If I had this here, what is this equal to?
1 x squared.
Oh, the antiderivative. I got it.
Oh.
Very nice.
Oh, that was important. You this? You got this, or you need another one? You got this?
You just did the antiderivative.
I just did the antiderivative. Okay? Now, this is so, this isn't correct here. If I have f prime of x like this equaling f of x, that's showing here. What do I need back here?
C.
Plus c, okay? And see, that's why we did all this. So we've spent time doing this, okay? Now, what I'm saying here is that we have now this. You see that a at x up there? And we said that that was the integral from a to x of f of t dt. Right?
Mm-hmm.
Let me just check to make
Yeah.
sure and I've
Yeah.
got.
Yeah, that's right.
Right.
Okay, now, you see this over here? Now, in terms of what I've done over there, this here is actually equal to f at, just a second, how do I want to do this? Just a second. I need to look at. I'm gonna go this way. At this point, you can see that if I take well, let's go this way. I've got this from here. Now, if I take the derivative of this, I see that the derivative of this one here is equal to f of x. See, here's this, see right here? See
Is
this
it
right here?
f of t?
Yeah.
Mhm.
Well,
Is it f of t you're saying? Are you
Yeah,
going
f of
off the
x.
one off the board or the one on the overhead?
that'd be good.
If you're doing the one off the board, it
But,
This here, no, this should be x, because I'm going up to here.
so it shouldn't be f of t then?
No, it shouldn't. It shouldn't. Because over here you see I have f prime at x is equal to f at x.
So the f of t should be f of x instead
so,
of.
yeah, why is the f of t in the formula and the f of
Um,
x?
I think I'll get there yet today. I'll show you how that goes too. Okay, there's, okay, yes.
Didn't you reading it, isn't like the variable that you're going up to, and then f of t is the actual function?
Yes,
Okay.
okay, listen to what he said, if that will satisfy you. Because up with, right here, notice, here is the t, but here is the a at x. Okay? Now, a couple of things here yet. With this in mind, now, this is what I want to accomplish. And we'll take another look at it on Wednesday. I would like to go from A to B, not just, not to x over here. And when I do f of x like this, this is, dx, this is going to be exactly equal to f at b minus f at a. In other words, we are saying this is an area ID. Now look what happens. This is the second part of the theorem, and it says this. I want to prove this now. I'm up to this part of it. I don't have this yet. I do have this. Okay. Now, I know that a at a is going to be equal to. By the way, we have this up here and this up here. And so you see this, just a second, how do I want to write this? That's okay. This is okay. The antiderivative of this happens to be f of, okay, just a second. I don't want that. Right here. This here implies that a at x equals f at x what?
Plus c.
Plus c. Now, everybody watch for this moment, because we're going to be shifting from some of the stuff we have to c, because c is going to disappear in a moment. It's just going to go. Yes?
Is this just background of doing the actual proof?
No, we're continuing going.
With the proof?
Okay?
Yeah, I'm so confused.
Okay.
I'm just-
Now I'm up to this point, and I have shown you
Would you
that
time
this
it?
here is equal to this. Okay? Now hang on here a minute. Look what happens. what is A at A? Little a. In other words, that's way over here.
F
Right here.
A plus C.
Did you hear that? F of A plus C. What is A at B?
F of B plus C.
You just do.
Okay, now,
How do you get that?
okay. You have a problem with this line?
Yeah.
Okay, I got that because over here, I said this f of x is equal to this. But I also know that this f of x here is capital F prime. See, like this.
Okay.
See, now, if I could have had another C over here, that might have, I don't know if that's confusing or not.
No.
Okay, now are you with me over here?
I think-
Okay, now look what happens. So with this in mind, I get A at B minus A at A. That's set. Now watch what happens here. This isn't hard, and you'll see in a moment. This gives me F at B
Mine.
plus C.
Okay, minus
Okay, Grant, go ahead.
F at A plus C.
So the C's cancel,
Wait,
so it's
so
F
minus C?
Okay, he wants it done this way.
Okay.
Because then you
Okay.
mix it up.
2C.
Oh, now look what happens here.
No.
We got two little details, and they're both easy. You'll notice this is minus the quantity, so this C and this C disappear.
Yeah, that's what.
Okay, now, this is F at B minus F at A. See that?
Yep.
Okay, but now, over here, you'll notice that what is A at A? 0. A at A is 0. Okay? And so that's 0. And so this is A at B.
Why is that?
What?
Because this is, okay.
I'm confused. I got confused.
Okay.
Okay, gotcha. Got it.
Okay, now, we have also said this, now see what happens here. This is that integral from A to B of f at x dx.
No.
Yes.
Why is f of a and a of a 0?
Okay. Why is this 0?
Yeah.
Because my curve over here, right here, see, there's nothing. This is the starting point. See, I'm starting here, so this thing is actually shoved right up against there. Okay? So there is no area at that point.
Makes sense.
Okay? And now, we've got to do a little bit more work yet in terms of flushing out what we have here. Okay? Now, we got a lot accomplished, but a couple things I'd like to do, and then we'll spend some more time on this on Wednesday so that you see what happens. But let's do a couple practical little things. Now, the first one I'm going to do today is going to be very easy. In fact, you're going to think it's ridiculous. Okay? And it deals with problems on the bottom of page 339. Is that the one I want? No, that's not the one I want. I want 341. 341. And it says this. Use that first part we have of this. We have the integral from 1. Oh, let's see. What did I do to my own?
Which one are you doing? A?
On page 341,
Yeah.
example 5.
A.
Yes, but I'm going to do, I just put an X, or T, dt here, like this, and I'm going to go from 1 to X, like this, and now,
Isn't it sign?
pardon?
It signs.
It says a sign, I want to just do it this way, it's easier.
Okay.
Okay? And he says now, what happens when I take the derivative of this with respect to x? And what happens there, this turns into nothing more than just an x. Because you see, these two are inverses of each other.
They are.
Yes.
Yeah, they are.
Sure.
Okay, and see this t turns into just a plain old x.
That makes sense.
Okay?
Yes, it does.
Yeah. This is that first one that I did, the first part of it. Okay? Now, let's see, the next one he did was, we'll just do the one he has there. The derivative with respect to x of 1 to x sine squared t dt. Okay?
So the
Now,
Equals sine x.
sine squared x.
science here.
Okay? Now, I'm going to do another one tomorrow, or Wednesday, that's a little trickier than this. And now, okay, there's a lot of loose ends that we're going to clean up this week. And here's another one. Now I'm going to use the second derivative. And you've been doing some of these already. This is the fundamental theorem of the calculus, part 1. Part 1. And we don't use it very often. Very seldom. Although both this book and the previous one spend a little time with it. So we'll do a few. That's all that this is. I will show you that there's a little bit more to it, but not a whole lot. Okay, now let's just do this one. If this were going to be x dx, and we're going to go from 1 to 2, what is that equal to?
8.5.
And there we go, x squared over 2, and we evaluate it from 1 to 2. Okay? Or in other words, we,
Yep, that makes sense.
okay,
Using the
now,
antiderivative.
let's do it more like the theorem says.
Yep.
I have f at x equal x. So f at x is equal to what?
X squared over
That
2.
one, it's there.
Plus a constant.
Up
Yep.
yonder.
Okay? Now, so this thing right over here, from what we have done, should be equal to 1, 2 to x dx is equal to f at
X.
2
What?
minus f at 1.
What? Are you doing the interval for that then? Or?
I'm making it a lot harder than it has to be.
Yeah, you
Yeah,
are. I
Okay?
don't like
This
that.
here is x squared over 2.
Minus x over 1, which is.
Yes.
8.5.
Okay? Now, this here, so this is going to be equal to x squared over 2 evaluated from 1 to 2.
Yeah.
Which gives me 4 over 2 minus 1 over 2, which is
3/2.
3/2.
Hooray.
Okay, now, again, all of the stuff we've been doing, we'll get a little more idea of it. Here's my function. This is f at x equaling x. Okay? And I'm figuring out how much I'll get here from 1 to 2. I'm figuring out this area. These Riemann sums right in here. Okay? And how big is that? Well, this height is 1, this height is 2, so the average is, I'm using geometry now,
1.5.
3.5, or 3 halves. And how wide is this? 1.
1 times 3/2.
Okay, now,
So that's the area of that one then you're saying?
yes,
Okay.
okay, now,
Mr. Kramer, will you be here Wednesday morning?
how many would like me Wednesday morning? Yes, I'll be.